Okay, so let's look at our first example. All right, we want to prove if A and B are both even, then A plus B is even. So let's go back and think about what method we're trying to use here. So this is an if-then statement. We're trying to prove P implies Q. Remember, the technique here is to assume P is true, and then we're going to show that Q must be true whenever P is true. And so let's go back to our statement, and I sort of identify P and Q here, right? So remember, P is the first part, so it's the part after if but before then. So oops, just this part. So here's P, and then Q is here. And so we want to start with assuming P is true, which is saying that A and B are even. So we'll start assuming A and B are even, and then we want to end up showing that A plus B is also even. So let's see how this goes. So this is a little sort of etiquette we're following here. We're going to state that we're starting a proof. And then the first line of the proof, I'm just going to write in English, assume A is even and B is even. Okay, so we're just assuming that P is true. We want to show that this forces Q to be true. So in the end, we want to say something about A plus B. But before we do that, in order to say something about A plus B, we're going to translate this into algebra. And so we actually have two statements here. One A is even and one B is even, and we need them both to be true. So start with the first one. So A is even. So then we'll say, A being even must be equal to 2k for some k that's an integer, and B is even, so B must also be a multiple of 2. We don't want to use k again for our sort of any integer, because that would make A and B equal to each other, and that's sort of a smaller statement than the one we're given. So just pick another letter. I'm going to use M. So B is equal to 2M for some M. Okay, so now we have this this is our translated into algebra. Okay, so we use this algebraic translation along with the statement we're trying to prove to come together. So the statement we're trying to prove, let's go back. The thing we want to end up showing now that we've assumed that P is true is that A plus B is even. We'll show that Q is true every time P is true. So A plus B. So we need to say something about A plus B. So just to give like a transition word, now A plus B, we know something about A plus B now because we have been able to rewrite A as a multiple of 2, and B is a multiple of 2 also. And so we're going to use this translation to say something about A plus B. So I'm going to replace A with 2K, and I'm going to replace B with 2M. Okay, so what do I need to show in the end? So I'm almost done, really. I've added two even numbers together. Here's the form of the first one. Here's the form of the second one. K and M, we want to leave as letters because we want them to stand for every possible integer, and that will give us every possible even number. But what do we need in order to say that something is even? So remember that evenness algebraically is defined by the fact that I can factor a 2 out. So even if I have a lot of stuff added together, as long as I can factor a 2 out of the whole thing, the stuff added together, since they're all integers, will remain an integer. And this 2 out front is telling me that everything's a multiple of 2. And so being able to divide the number by 2 is telling me that it's even. So notice that we have that scenario here. I can take a 2 out, and I'm left with K plus M. Since K plus M is still an integer, we know that A plus B is even. And so, and in the end, we want to say, sort of end this. Usually, the modern way is just to put a box to show that you've ended the proof. So, notice that we've ended with a statement Q. We've started with the statement P, and in between, we have used algebra to show that Q is true given A. Okay, so here's the sort of algebra work. This is P is true. And then we end with Q is true.